Welcome to the second week of our solar energy course on photovoltaic materials, devices and modules. In the previous week we discussed the various crystalline silicon PV device architectures. In this week and the next we'll discuss the various thin film PV technologies. But before we do, we will discuss some concepts that are important for more than one of these technologies, such as the PIN junction, light management in thin film solar cells and multi-junction solar cells. Additionally, in this video, we'll discuss a class of materials known as transparent conductive oxides, or TCOs. The learning objectives for this video are to understand the function of the transparent conductive oxide in a thin film solar cell and the material properties and performance of TCOs. Finally, we will consider the materials used for TCO production. Let's start with why TCOs are used. In the figures, typical architectures are shown for a wafer-based device on the left and a thin film PV device on the right. The TCO layers are indicated in green. As we well know, charge carriers generated in absorber layers of these devices are separated and collected at the front and back electrodes. If we assume the P layer to be at the front side of the cell, holes are collected at the front electrode, while electrons are collected at the back electrode. The back electrode often covers the entire back surface of the solar cell. The front electrode, however, only covers a very small portion of the front surface in order to minimize shading losses. Many materials used for thin film solar cells have a relatively poor lateral conductivity due to the thin film deposition techniques and growth direction of the materials. This makes it challenging for generated and separated charge carriers to be collected at the front electrodes. Thin film solar cells therefore often require a layer at the front of the device that is both highly transparent to incident light and also has high lateral conductivity. There are several materials that could act as such a transparent front electrode. We can consider, for instance, the use of a very thin metal sheet of only a few nanometers thick. The transmittance of such a metal sheet is plotted in this graph as a function of its resistance. The metal film becomes less transparent and more conductive as the film thickness increases. The same trade-off between conductivity and transparency is observed in some more exotic materials like carbon nanotubes. However, transparent conductive oxides can achieve much lower sheet resistance for similar transmittance values. A TCO is a metal oxide mixture with a wide band gap. The optoelectrical properties of TCOs depend on the nature, the number, and atomic arrangement of the metal particles in a material and on the presence of defects. The defects can be intrinsically present or purposefully introduced by doping of the material. Let's look at the TCO material properties in some more detail. Shown here is the optical performance of an aluminium-doped zinc oxide layer with a thickness of 880 nanometer used as a front transparent electrode. The red area represents absorption and the yellow area represents the reflection by the layer. Blue indicates the transmission through the TCO. We can divide this spectrum in three parts. For short wavelengths, the photon energy exceeds the TCO bandgap energy, leading to very high absorption by the TCO layer. For energies below the bandgap energy, the transmission through the TCO is very high. In this part of the spectrum, we can see the interference fringes of the TCO layer that can be used to determine the layer thickness. After a broad, highly transmissive wavelength band, the absorption increases again. This absorption is called free carrier absorption and can be explained with the Drude model of metals. The Drude model of metals will be discussed in the next video, where we continue our discussion of transparent conductive oxide layers.